Hello, and welcome back to Calculus 2. In this lecture, we're going to be starting Chapter 11, the final chapter that we'll be talking about together in this Calculus 2 course. So we're going to start off, of course, in section 11.1, which is called sequences. So you're looking at the goals that I've written there in this lecture. Let me kind of just highlight them for you as we start. I want to take a few minutes, not too long because I don't want these videos to be too long, but I want to take a few minutes to motivate why are we talking about sequences in calculus. It's going to feel like a little bit of a subject change here as we move into chapter 11. For a while, derivatives and integrals are going to kind of drop into the background, and we're going to be starting to talk about these things called sequences and then later a series. So I want to at least motivate why are we switching the subject here? Why do sequences come up in calculus? Okay, so once we have that motivation in hand, then I want to just introduce what I mean by a sequence and get used to some of their notation. And sequences, like functions, have limits. In this first part, I'm just going to kind of informally define limit. I won't give a formal definition of it, but I want to give you a sense of what it means. A sequence, like a function, has a graph, and it has a limit as its input goes to infinity. And so I want to check that out informally, hopefully looking at lots of examples. Okay, so that's our goal. We're outlined. Let's see if we can get it done here. So here's the motivation I want to give you. All right, so among the many kinds of functions that we look at in mathematics, calculus in particular, some of them are polynomial functions. You know what a polynomial function is. I'm not going to try to define it here. I've just got an example. There's a degree 2 polynomial function, x squared plus 3x plus 7. All right, and my point is that when you want to evaluate such a function at a number, when you want to plug in a number, here I've plugged in the number 1. Well, when you do that for a polynomial function, you do arithmetic, right? You replace the variable x with the number, in this case 1. And then what kinds of things do you have to do? Well, you have to be able to square that 1. That's arithmetic, 1 times 1. You have to multiply 1 by 3. That's arithmetic. You have to be able to add all of those things together. More arithmetic, 1 plus 3 plus 7, I think it's 11. So evaluating a polynomial function, you do it with the operations multiplication, addition, subtraction. Polynomial functions don't even use division unless some of the coefficients are fractions, but they're arithmetic functions. Yeah, you evaluate them with arithmetic. Well, compare that to some function like a trigonometric function like sine. Yeah, here I'm thinking x is an angle, it's measured in radians, so it's a real number, like 1. 1 radian is an angle on the unit circle that's just a teeny bit less than 60 degrees. You can put it into your calculator. You can pause this video right now if you want, put your calculator in radian mode, type in sine of 1, and it'll give you some decimal. It'll give you some decimal. It's going to be, I don't know, around 0.6 or something like that. But my question is not what sine of 1 is, but really I'm asking the question, what is your calculator doing when it computes the sine of 1? Like what's it plugging the 1 into? Because, you know, at the end of the day, as fancy as your calculator seems, all it can really do is arithmetic. It can multiply, divide, add, subtract. It can do it very well. It can do it with decimals and blah, 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 but it does arithmetic. So how does it calculate the sine of 1? Does it have a little unit circle hidden in there and it measures off an angle of 1 radian and finds the y coordinate? I don't think it does any of that. It's doing arithmetic, okay? So I'm going to show you some polynomials here, some polynomials I wrote in my messy handwriting that I know. I'm purposely kind of trying to tease you here because as we launch into chapter 11, I'm going to show you how you could find some of these polynomials. But for right now, I'm just pulling these things out of thin air. And I've written down 4 of them, and I gave them kind of weird names, P1, P3, P5, P7. So you'll notice I'm kind of skipping even numbers. That's because I'm just putting the subscript so that it matches the highest degree of x. All right. So I won't say anything else. I'm not telling you where I got these polynomials. Maybe before I started the video, I went down to the polynomial store. Well, actually, I couldn't do that right now because the polynomial store is probably closed due to the coronavirus. But maybe before all of this, I went to the polynomial store and I picked up these polynomials, and these were their names, and there they are. So I'm going to switch over. I'm going to change my screen share here for a second. I've got a Desmos window ready for you, and we're going to look at those polynomials. All right. So you don't have to write them down right now. Just remember that there was a degree 1, a degree 3, a degree 5, a degree 7. So let me show them to you. Okay. So your screen should be switching. Is my screen switching? I don't know. Just give me 1 second here. There, you're probably looking at it. I hope you are. And what I've got, ignore all this business on the left, okay? That's my business. That's what I got at the polynomial store. But what you're looking at is a graph of P1. And if you remember that P1 of X was equal to X, that graph looks totally reasonable to you. That looks like a graph of the function of P1 of X equals X, line, slope 1 through the origin. So if I move this slider, if I change the value of M to be the next value, there's your P3, okay? That looks like a cubic polynomial. P3 was a cubic polynomial. Why am I showing you these? It's sort of a random thing to do. There's P5. That's a 5th degree polynomial. You can count its bumps. 1, 2, 3, 4. 4 bumps, 5th degree polynomial. Here is P7. It's harder to see that that's a 7th degree polynomial, but just trust me, that's a picture of P7. And then I didn't write them down in the previous screen. Those denominators get kind of out of control, but I'm just going to keep showing you more and more P's. All right, here's P9. That would be P11. Yeah, P11. There's P13. Let me just kind of do this here. Just making the degree higher and higher. You don't know the formulas for these polynomials, but you're seeing something kind of interesting, that they're changing a lot out on the ends when I increase this M, whatever this M is doing. But in the middle, the pattern is getting kind of stable. And in fact, that stable pattern kind of looks familiar to me. If I turn on this tag, the sine function, remember I was trying to compute the sine of 1. Let me show you this thing again as I do this. That sine function there is drawn in green, and these polynomials, they're kind of wrapping around the sine function. So somehow I know how to write down polynomials that will get closer and closer to the value of the sine function, well, at least for some values. You know, way out here in the picture, they're not all that close. So this is my motivation. How did I find these polynomials? What am I doing? All right, so let's switch back to our whiteboard where we can all see what's going on. Give me a second here. There it comes back. All right. So yeah, you're supposed to be sort of mystified. Why do these polynomials do that? Well, plot spoiler, your calculator knows these polynomials. And when you plug in something like sine of 1 into your calculator, it's really just taking one of these polynomials, probably a bigger one than P7. And I'm simplifying this conversation a little bit. Your calculator might have some fancier techniques, but for our purposes, you can just think that your calculator takes one of these polynomials and it plugs 1 into it. And those graphs we were just looking at in Desmos should have convinced you that, well, yeah, that polynomial's value at 1 is going to be darn close to the sine of 1. In fact, we'll say more that we can make it as close as we want. So I'm talking a lot about the motivation. We haven't even started our work in section 11.1, but let me just show you one kind of summary of this. This is to kind of keep you motivated. The goal of the entire chapter 11 is to show you how to generate those polynomials. They're called Taylor polynomials, named after an English mathematician called Taylor, who wrote about these kinds of things. Yeah. So the whole goal of chapter 11 is to be able to get you to a point to where I could say, hey, the function is sine of x, and you can write down those polynomials. You know, there's a lot of questions like, what about these numbers? 6, 120, 5040, where are they coming from? Why am I skipping even exponents when it's the sine function? Tons and tons of questions. Chapter 11 is a long story to answer those questions. We won't accomplish our goal until we get to the 10th section. All right, so there's a lot of preliminary material that I have to walk you through in order to be able to understand what these polynomials come from. And some of the preliminary material is going to be a little bit unfamiliar, and it's not going to feel a lot like calculus. So I'm spending this time in this video so that you understand what it is I'm trying to do. My end goal is that you could generate those polynomials. You can approximate any function that you want with polynomial functions, arithmetic functions, okay? So I hope you're motivated because it's time to start our work. Our first topic is something called sequences, and that's what we need to start with to take the first step on what this long journey will be towards these Taylor polynomials. All right, so let's get to work. It's a sequence. Well, let me tell you what a sequence is. A sequence is just an infinite list of numbers. It's got a first number. I'm denoting it by a sub 1. The subscript is just kind of telling me which position in the list I'm at. We call those the terms. A sub 2 is the second term. A sub 3 is the third term. The nth term of the sequence, a sub n, where n is some variable. I've got some dots here to indicate that this list has no end. It's an infinite list of numbers, and an infinite list of numbers is called a sequence, okay? There's different ways to write this sequence down. Different notations. One notation is you just write the list. Yeah, you certainly can't write all infinitely many elements of it, but you can write the list until a pattern emerges. And we typically enclose sequences in these things called set braces, okay? Another way to do it is to just give me some function, give me a formula for the nth term. I'm writing it f of n just so that it makes your brain think, oh yeah, there's some expression that I would plug n into to give me what the nth term is. And I can just write that expression inside these set braces. And then I'm obligated to tell you where n starts. For most time, it'll start at 1. It doesn't have to, but you have to write that n starts somewhere. This is like summation notation, yeah? N starts at 1, and then we just write that it goes to infinity. So that's sort of an alternate notation for a sequence. Okay, let's look at some examples. I think I'm ready for some examples. I'll try to leave that in view as we start this first example. So I'm going to write a sequence, and I'm going to write it just by start writing out some terms. My sequence is going to go like this: 1, 1/2, 1/3, 1/4. You have quote unquote caught on to the pattern, or you understand the nth term of the sequence as soon as you can kind of predict to me what I'm going to write next. You're not here to answer this, but I bet you can predict what I'm going to write next. Can you do it? Say it out loud and maybe I'll hear you. I'm going to write 1/5. Yeah, so I'm generating this sequence one term at a time. So now what I'm going to try to do is write down, well, a formula for the nth term. What does the nth term look like? When n was 1, it's 1 over 1. When n was 2, it's 1 over 2. So the nth term of the sequence is just the number 1 over n. So there's my sequence written out as an infinite list. Or to use this more convenient compact notation, I'll just write that this sequence is the sequence of things that look like 1 over n, and then I start n at 1 and I let it go all the way to infinity. So here is my so-called formula for the nth term. If you want me to write it, a sub n is 1 over n. The formula for the nth term of this sequence is 1 over n. Okay? Cool. So I'd like to look at another screen. Sequences have graphs. People don't usually call them graphs. They call them plots. So what do I mean, plot this sequence? Well, I don't really mean anything much different than what I mean by a graph. I'm going to look in the XY plane at pairs of points, but I'm only going to let the input coordinate be a whole number. So 1, 2, 3, I'm not going to let it vary continuously like x, like a real number. And then in the second coordinate, I'm just going to plot whatever the sequence value is. Yeah. So for this sequence, if we'll look at a plot here in a second, but I'm going to plot points like 1, comma 1, 2, comma 1/2, 3, comma 1/3. So the first coordinate is always the position in the sequence. The second coordinate is whatever the sequence value at that position is. All right. Let me switch over to Mathematica. I generated a Mathematica plot. I'll show you at the end of this lecture how you can do this on Desmos, but I'm going to do it in Mathematica. So I've got a plot ready. Let me switch to it. Okay, can you see it? I hope you can see it. Otherwise, this is going to be kind of an awkward video. But so I got a lot going on in this slide. Let me kind of narrate it for you. Ignore my Mathematica code, unless, of course, you're trying to learn some Mathematica. That's how you can generate some terms in the list of a sequence. So I've just written that I want a table. That's a Mathematica command. And then I put 1 over n, my nth term. And then I told it what I want n to do. A Mathematica can't show me infinitely many terms, but it can show me as many as I want. And I had it show me 20. So here was more than I was willing to write, but I've got, yeah, 1, 1/2, 1/3, 1/4. I think I went out to 1/5. Here I'm showing you the first 20 terms of this sequence. Some of your homework in this first part of this 11.1 is just going to give you a formula for the nth term and ask you to write out the first few terms, the first 5 terms of the sequence or something. So if this homework problem were given the sequence 1 over n, write out the first 5 terms of it, I'm going to write those 5 numbers in a list. Okay, and I don't need Mathematica to do that. I can do it by hand. Here's a plot. Again, if you're interested in the Mathematica code, I'm going to show you how to generate such a plot on Desmos towards the end here, but Mathematica plots a sequence with a command called listplot. I'm talking too much about Mathematica. Let's just talk about the sequence. So what are you looking at in this picture? This dot that's y coordinate is 1. It corresponds to the sequence term 1. It's drawn above n equals 1 on the axis down here. All right. And then there's a dot whose y coordinate is 1/2. It's drawn above n equals 2, and so on. So that's a plot of this sequence, all right? Or at least a plot of the first 40 terms of this sequence. Cool. So what's a graph of a sequence? It's basically like the graph of a function, except you're skipping the input values that aren't whole numbers, okay? You're skipping over the input values that aren't whole numbers. Okay. So I want to informally define something that's called the limit of a sequence, and I'm going to use this picture while we're looking at it. Notice that as we increase n, as we look further and further out to the right, the y coordinates on this sequence are all getting smaller and smaller. They're all positive, but they're getting closer and closer to 0, right? The y coordinate of this last one is a 40th. If I've got Mathematica prepped to convert these fractions into decimals, if you like, the first 20 of them here, I don't know if that's all that useful, but if I change this to a 40, I could tell you a decimal approximation for that last number. It's 0.025. And as we look further and further out in the list, maybe I can change this 40 to 100. The scale is making it a little bit harder to see, but look, the further and further, we were only going to 40. Now I'm only going out, I'm going all the way out to 100. The terms in the sequence are getting even closer to 0, right? This term out here, 1 over 100, that's 0.01. If we went further out, this will be kind of a ridiculous picture, but if I look at the first 1,000 terms of the sequence, look, after 200 or so, it's hard to distinguish them from the y equals 0, the x-axis. So what am I going to say informally? Let me switch back while I'm saying this so we don't have to wait so long. Oops, sorry about that. What am I saying? I'm saying that as I look at larger and larger values of n, the terms of that sequence, the y coordinates in that plot, if you like, are getting closer and closer to 0. So from that plot, here's what I'm going to write down. So from the graph that we were just looking at, you can rewind the video and look at it yourself or look at it again. I'm going to write down, this is going to be our notation. Familiar looking, limit I'm going to say as n goes to infinity, because n is the input value for our sequence. And then I just write the nth term. And just from the plot, it looked like the further and further out, the bigger and bigger we took n, the closer and closer those sequence values got to 0. So we'll write something like this. The limit as n goes to infinity of 1 over n is 0. I'll try to make a more formal definition of that in the second part of this lecture, which we will do on Monday next week. But for right now, I'm just going to say, well, the plot made it look like that. And for some language, we're going to say that the sequence, this is just some lingo, we're going to say that the sequence 1 over n, as n goes from 1 to infinity, converges. So we're going to use similar language that we did for, say, improper integrals. Yeah, when the limit exists, the sequence converges to 0. Okay, so if a sequence has a limit, I'll say it converges. Maybe you remember from improper integrals what we say if something doesn't have a limit. We'll use similar language here. We'll call it divergent. This sequence is convergent, converges to 0. Cool. Well, if we were all in the same class at the same time, I'd ask you if you have any questions, but you can just ask me questions when we're all online at the same time. I think you guys are probably taking your midterm right now, or at least I hope you're taking your midterm right now. Okay, let's look at a second example. Let's get a second example. I'm going to just kind of run through the same thing. I want to write a list, kind of get you to think about how to write down a formula for the nth term, and then I want to look at a plot and see if the plot can give me some guess about whether or not the sequence has a limit. Okay, let's try it. Clean slate, new list. Here we go. I'm going to start writing my sequence terms. As I'm writing them, you can play the game. Can you guess what I'm going to write next? As soon as you can, then you understand the pattern of this sequence. So here we go. I am going to write the number 1/2, and then the number 2/3, and then the number 3/4. You got it yet? What am I going to write next? Did you say 4/5? Good. Yeah. What am I doing? Each time I generate a new thing, I'm taking the denominator from the previous one and I'm making it the numerator, and then I'm taking the new denominator to be one more than that. All right. So if we think about how to do that in general, the fact that we started with the numerator equal to 1, we're just taking a number, say n, and we're dividing it by the next number, say n plus 1. It's not the only way to write this down, but it's one way. And I think because this is a video lecture, I'm just going to leave it to you to ask me in class if there's other ways to write that down. But there's this sequence, and we understand the nth term. The nth term is n over n plus 1, and that's valid for n at least 1. So if we want to write it in our shorthand, I would write, well, it's the sequence of n over n plus 1, and then let n go from 1 to infinity. Or if you want to explicitly write what your nth term is, your nth term is n over n plus 1. Okay? Cool. So I have a similar question. I would like to know, well, what's going on as n goes to infinity? Maybe you can just answer that question. Looking at that expression, we have some experience with limits. You know, if I was asking you the limit as x goes to infinity of x over x plus 1, I bet you could tell me what it is. And in fact, this question has to have the same answer, because after all, these a sub n's, you know, if we plotted the function, say f of x is x over x plus 1, then these sequence values are just the y coordinates on that graph where the input coordinate is a whole number. So if you can answer this question, if you can answer the question, what is the limit as x goes to infinity of x over x plus 1, then you have also answered my question about my sequence, because, you know, if the entire curve is approaching some number, well, then so are the dots that are above whole numbers. That's kind of actually a very powerful way to think about limits of sequences. I'll call this thing, I wish I would have left some more room to write its name. I'm going to call it the associated function. Yeah, the associated function is just the function where you let the variable vary continuously. And whatever happens to the associated function, the sequence has to do the same thing. Let's go back to Mathematica and look at a picture. So which one is Mathematica? You say, what are you talking about? You don't see what I'm seeing. Here comes Mathematica. I've got example 2 all ready for you to go here. I wrote the table out in Mathematica a little bit further than what I was willing to write by hand. But yeah, those numbers, 4/5, 5/6, and so on and so on. So what are they approaching? Well, you could look at them numerically, but I mean, this numerator and denominator, the difference between them is becoming less and less. Yeah. So if you start going out in this thing, if you want to look at some decimal approximations, that last number, 20/21, is 0.95. So fractions whose numerators and denominators are close to each other are approaching 1. Here's the list plot of it, the plot of the sequence. So you can see that these sequence terms, unlike our previous example, the y-coordinates are getting bigger as n goes to infinity. So the sequence terms are increasing, but they're not increasing without bound. They seem to be approaching something. And if you look over here on the y-axis, it looks like they're approaching 1. I drew a plot with the sequence terms in it, and then I just drew a red line where y is equal to 1. And yeah, that plot is rather convincing that it looks like this sequence has limit equal to 1. I'm only looking at 20 terms. Let's go up by an order of magnitude. I'll show you 200 terms. That didn't work very well because I also have to do that. So when I'm looking at this picture here, what's it telling me? It's telling me, I mean, that it looks like a curve. Those are really dots. There's just so many of them. They're so close together, they get smashed. You can see the dots over here. But yeah, the further and further we look out, look, that blue sequence of dots becomes indistinguishable from the line. So all of that is what is justifying me when I write down the following. This thing comes back. The delay is a little bit awkward, but yeah, it looks to me that the limit of that thing was 1. And if you said the limit of this function is 1 because it's a polynomial over a polynomial whose degrees are equal, or maybe you broke out L'Hopital's rule, there's lots of ways. You were absolutely right. Good. All right. So we're doing pretty good. We're doing pretty good. Let's try it again. Okay. I've got some other sequences I want to show you. Ready for the pattern? Let's go. Here's my pattern. 1 minus 1. 1 minus 1. Got it yet? Good. Yeah, I'm just alternating. 1 minus 1, 1 minus 1, 1 minus 1, back and forth, over and over and over again. So how do we write that as an nth term? How do we get signs to alternate? Well, one way to do it, a very nice way to do it, is to just think about powers of -1. Powers of -1. Because as you take powers of -1, if you have an even exponent up there, you get 1. And if you have an odd exponent, you get -1. So my first thing I want to try is just to put an n up there. Call this the nth term. But that doesn't quite work because when n is 1, if this is the first term in the sequence and I want n to be 1, well, -1 to the n is not 1, it's -1. And then when n is 2, -1 squared isn't -1, it's 1. So I've exactly got the signs backwards. So there's different ways to fix this. I'm going to fix it like this. I'm going to just increase my exponent by 1. All right. So I'm going to write this sequence down as saying, well, it's the sequence of terms that look like -1 to the n plus 1. And I start n at 1 and go to infinity. Because now when n is 1, n plus 1 is 2, and that'll give me the sign plus, and then they're going to alternate. All right. So my formula for my nth term in this case is -1 to the n plus 1, and I'm letting n go from 1 to infinity. Cool. So the question is, well, what's the plot? We could look at Mathematica. Let me show you how you can use Desmos to generate graphs of sequences, all right? Because that's a tool that you might have a little bit more access to. I'm kind of a new sequence plotter on Desmos, but let's see if I can convince you that I've learned how to do it. So I want to find my Desmos window. I've got a blank one kind of waiting for us. That's not it. Let's see. I don't know what you're seeing right now. Sorry. I'm looking for, oh, I think I just closed the window that I want. Here, let me come back here so that I know what you're seeing. Sorry, this is a little bit frustrating. You can skip forward in the video if you want. I'm just trying to find a new Desmos window in my browser. So now I've got one, and let me bring back you guys. Can you tell that I make these videos on the fly for you, and I don't know how to edit? Both of those things I think are very clear. Let's see. I hope that you can now see this Desmos window. If not, then the next part of this share is going to be, or this video is going to be unintelligible, but assuming you can see it, assuming that you can see this Desmos window, what have I got going on over here? I've got the usual Desmos pane, and I wanted to plot the sequence -1 to the n plus 1. Okay, so here's how I'm going to do it. I'm going to first tell Desmos that there's a function, a of x, I'm going to call it a of x, and then I'm going to just put that a of x is -1 to the x, all right? And that'll kind of confuse Desmos because it doesn't know how to treat x as a continuous variable there, so I'm just going to hide that function, okay? And now I'm going to tell it that I want to just look at points. I want to look at points. I'm going to call them n comma a of n. And it's confused right now because it doesn't know what n is. And I don't want to add a slider for n because if I do that, it's going to only show me one sequence point at a time. Okay, so you might have to watch this part of this video a couple times, but you can just follow these steps. My last step is I'm going to come down here and say, look, I want n to be a list. I hit a square bracket, and I type 1, comma, dot, 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 comma, and then some other letter. I'm going to call it capital N, okay? Close that bracket, and yes, I do want a slider for capital N, and then I click on that, and I want capital N to start at 1. I want it to go to something reasonably big, like 50, but I don't want it to take on values in between whole numbers, so that's what that step size does, okay? So now if I come over here to the graph, let me just move it so that we're seeing. What it's showing me is the first, sorry, this needs to be more, I wish I could edit videos. X plus 1 I needed X plus 1 to be my A. Good. So now what is this dot in this picture? It's the first term in my sequence. It's R1. And now watch this. When I start moving capital N, it's going to generate more and more sequence terms. There's the 4th term, 5th term, 6th term, and so on. Okay. So there's a picture. Maybe it wasn't worth it to draw all this of what it looks like to plot a bunch of 1s and -1s. But I did want to show you how to generate a sequence in Desmos, so that's handy. And so looking at this picture, what about this limit? Yeah. Is it like those other pictures? Are these dots getting closer and closer to some value? You might be tempted to say, well, they're getting closer and closer to 2 values. Yeah, if we just plot, say, y equals 1 and y equals -1 on the same screen here, let me maybe change the color, those things. Make them both red. You might be tempted to look at this and say, yeah, Dr. Evans, I think that that sequence has 2 limits, but a sequence can't have 2 limits. if we're going to write that the sequence has a limit, there has to be one and only one number that its values get close to. And here, this sequence is trying to be close to two different values. It's trying to be close to the value 1 and -1 as we go out. So it doesn't have a limit. So let's switch back to the whiteboard and write that down. Switching back to the whiteboard. Should be coming back. Yes, good. So we looked at the plot. I can just sort of crudely sketch it here again, but this sequence went 1, -1, 1, -1, 1, -1. Tired of me saying that. So the limit as n goes to infinity of -1 to the n plus 1 does not exist. It doesn't have a limit. So the language that we're going to use is we're going to say that this sequence, -1 to the n plus 1, diverges. Yeah, when the limit doesn't exist, it diverges. So not all sequences have limits. Cool. Okay, I know this video is getting kind of long. But let me at least kind of do a couple of more things here. Maybe if it's too long for you, you can pause it, go get a snack, and come back and try to watch the tail end of it. I hope you watch it because these are kind of integral parts of trying to continue our course. Okay, so let me look at one more example. I'm kind of stealing something like from your book. Your book is going to ask you to do a couple of problems like this. So here I have some sequence, a sub n, and I'm just going to tell you its nth term. It's the sine of pi over 2 times n. All right? And let's say that n goes from 1 to infinity. So if I wrote this thing down in my sequence notation, I would write just the nth term is sine of pi over 2 times n. And I'm going to let n equal 1 to infinity. And you'll be asked to write out the first, say, few terms. Let's do 3. Find the first 3 terms. Okay, so how do you do that? At the first term, a1, I replace n with 1. So I take the sine of pi over 2 times 1. That's the sine of pi over 2. That's 1. a2, I replace n with 2, so I take the sine of pi over 2 times 2. Well, that's the sine of pi, so that's 0. Yeah? How about a3? Take the sine of pi over 2 times 3. That's the sine of 3 pi over 2. That's -1. And so on. So you're going to be asked to do this. Let's flip back over to Desmos real quick, and we can look at many terms of this thing. This is why I want to teach you how to use Desmos to do this, so you can look at many terms. We don't have to reinvent the wheel. I'm going to just come back up here. Well, first of all, let me get rid of those two lines, y equals 1 and y minus 1. And I'm just going to modify this formula. All right, so I wanted the sine of pi over 2 times, remember I got to call it x in this formula so that Desmos knows what I'm talking about. And then I could pull my slider back, and here's the first thing that we found. Maybe I can zoom in a little bit. When we wrote on that whiteboard, a1 was 1. There's your a1. Here's your a2. We said it was 0, and sure enough, it's 0. There's your a3. I wish I could. Let me real quick. I do want to do this for the y. I'm going to make this like -2 to 2 so I can see this better. Good. There's a3, a4, a5, a6. All right. So let me ask you. You can't answer me, but I'm asking you anyway. Does that sequence have a limit? Does this sequence have a limit as n goes to infinity based on this picture? What do you think? I'll leave a big dramatic pause while I go back to our whiteboard. We wrote out the first few terms. In our language, we're getting used to some new language. I could ask you, does this sequence converge or diverge based on the plot? not the plot with an E, but just the plot, I would say that it looks like the sequence sine of pi over 2 times n, as n goes from 1 to infinity, diverges. Those dots were not getting close to some one value. Okay, one more thing I want to mention at the end of this. It's not really an example, but some of you may be familiar with this. Some may not. It's part of some of your homework questions, so I want to at least define what I mean by some of this notation. So what I'm defining is something called a factorial. And it's also a sequence. It's a sequence, and let me tell you how I can define it. A so-called well, let me just write it out. So if I take some number n that's at least 1, what I mean by n with an exclamation point, and you read this out loud, n factorial. N factorial is the product of n with all of the whole numbers that are less than or equal to n, stopping at the number 1. Okay, so let's practice it a little bit here. Like something like 3 factorial would be 3 times 2 times 1, or 6. Okay, 4 factorial is 4 times 3 times 2 times 1. That's 24. Maybe you've noticed that 4 factorial is 4 times 3 factorial. In fact, that's a so-called recursive way of defining the factorial function, as I can say, well, let's define 1 factorial to be 1, and then we'll define n factorial to be n times n minus 1 factorial if n is at least 2. So that's what I mean by the factorial function. So you can practice with some of these things. In a couple of your sequence examples, like I'm just looking at your book, I'm not going to do this, but one of your homework problems asks you to think about something like a sequence like a sub n is 1 over n factorial. All right, so if you write out the first few terms of that, a1 would be 1, a2 would be 1 over 2 factorial. 2 factorial is 1 times 2, or 2. A3 would be 1 over 3 factorial. I know I'm talking a mile a minute, but this video is getting long. All right, so we're going to work rigorously with sequence limits in the second part of 11.1, but this should arm you to do that first part of your homework. So I will see you in a Zoom meeting near you soon.